So in this lecture, I will discuss large deviations of IID random variables. So we will be considering in some probability space omega f and p a sequence of xn, n larger than 1, and I will assume that these random variables are independent and they are identically distributed. And more than that, I will assume that for all lambda in R, the expectation of the exponential of lambda x1 is finite. This is not needed for what I will prove, but it simplifies. And so I would like to present the proof in the simplest possible context. So we will assume that for any lambda, the exponential of lambda x1 it's integrable. And in particular, that means that for all k larger than 1, the expectation of the absolute value of x1 to the power k it's finite. And this is clearly because if you take x, the modulus of x to the power k, you can find a constant c which depends on k, such that ck exponential x plus exponential minus x, so that the modulus of x to the power k is bounded by this sum. And therefore, since I'm assuming for lambda equal to 1 and minus 1 that the expectation of exponential x1 and exponential minus x1 is finite, we get immediately that this expectation is also finite. And if you want to fix ideas, let me give you two examples of random variables which satisfy this inequality. And the first one will be the Bernoulli. So you fix p, let's say, between 0 and 1, and you assume that the probability that x1 it's equal to 1, that this is p, and this is equal to 1 minus the probability that x1 is equal to 0. So you have a random variable which takes two values, 0 and 1. It takes the value 1 with probability p and the value 0 with probability 1 minus p. And so these are what we will call Bernoulli random variables with parameter p. So this is a first example of a random variable which satisfies this inequality because, well, x1 it's bounded by below by 0 and above by 1, and therefore it clearly satisfies this bound. A second example will be to take a random variable x1 which is distributed as a Gaussian with mean 0 and variance equal to 1. So this means that the probability of x1 belonging to a set A, so A it's a subset of R which is Borel measurable, that this will be equal to 1 over square root of 2 pi, the integral over I of exponential minus x squared over 2 dx. So we are integrating over A this density. So you see that x1, the distribution of x1, it's absolutely continuous, and here is the density. And so this is another example. I leave it to you to check that indeed the expectation of the exponential of lambda x1 is finite for any lambda. So this will be the main assumption. So we have a sequence of IID random variables. These exponential moments are finite, and I will explain in the next take what we want. I'll first present a proof of what's called the weak law of large numbers, and then I will state the large deviation principle. So here are the main definitions and the main assumptions. Xn is a sequence of IID, and we are assuming finite exponential moments. So now I want to present the weak law of large numbers. Let me call M the expectation of x1. We know that it's finite from the assumption, and what I claim, and this is the weak law of large numbers, is that for all epsilon, positive, the probability that the average of x1 plus xn divided by n minus m divided by epsilon minus m, the absolute value larger to epsilon, I'll claim that this tends to 0 as n goes to infinity. So the claim is that for all epsilon positive, the average of the first n terms, x1, xn, minus its expectation that this is small. So that the probability that this is larger than epsilon goes to 0 as n goes to infinity. So let me prove that. So this is a theorem, say, and let me prove. And the assumption, the important assumption I will need here, it's a much weaker assumption than this one. I will be assuming that only the variable x1 has a finite second moment. So assume that the second moment is finite, so you know that the first moment it's also finite. Call it m, the expectation. And what I claim is that under this assumption, we have this result. So to be precise, we have a sequence xn of IID random variable with finite second moment. I claim that this is true. And the proof, it's very simple and uses the tools presented in these lectures. So let me first say that, well, the probability that this is larger than epsilon, it's equal to the probability that if I take the square on both sides, that x1 plus xn divided by n minus m square, that this is larger than epsilon square. Now I can use Chebyshev inequality to say that this is bounded by 1 over epsilon square, the expectation of these random variable, which is non-negative. And, well, I will write these difference as 1 over n, sum from j from 1 up to n of xj minus m square. So I just introduced m in the sum. And now I will expand this square. So I get, and I will use linearity to exchange the sum with the expectation. So this is the sum for j and k going from 1 up to n. I have here 1 over n square, and then the expectation of xj minus m, xk minus m. Now, let's use independence. If j is different from k, this expectation, so the random variable xj minus m, it's independent from xk minus m, so the expectation of the product is the product of the expectations, and the expectation of xj minus m, by definition of m, it's equal to 0. So this product, it's equal to 0 if j is different from k. So in this sum, only the diagonal terms will survive. And so this is epsilon square. We have n square. Now, the diagonal terms are of the type xj minus m square. But since the random variables are identically distributed, this becomes x1 minus m square. And I have n of these terms, n diagonal terms. So I have n, which represent the number of diagonal terms, times the expectation of x1 minus m square. But this is finite because I assumed that x1 has a finite second moment. So you see that this is equal to 1 over epsilon square times n, expectation of x1 minus m square. And this is clearly going to 0 as n goes to infinity. And so this completes the proof of this theorem. So we only used here the assumption that these variables have finite second moment. Fine. So this is quite simple, and this is called the weak law of large numbers. We are proving that in some sense this average or this sequence of random variable is small, so that the probability that it's larger than epsilon converges to 0 for all epsilon. Fine. So this tells me, so as a consequence, I get immediately the following. If I take number A larger than m, then the probability that, so let me call xn bar the average of xn. So that will be 1 over n, the sum from 1 up to n of xj. And so this is xn bar. And so if I take a larger than m, this result, it's telling me that xn bar larger than a, that this is going to 0. Because I can write a as m plus epsilon, and it will follow from this result that this probability is converging to 0. And the same thing, if I take a b less than m, then what we have is that the probability that xn bar smaller than b, that this is converging to 0 as well. And I can take here larger or equal if I wish. Well, what we are going to do in this lecture is to estimate this probability. We know that it converges to 0. What we will prove that it actually converges to 0 exponentially fast. And we will get a bound on the rate at which this probability converges to 0. So this is the main topic of this lecture, is to obtain an estimate for this probability. An upper bound for this probability will be proved in this lecture, and in the next lecture we will prove lower bounds for this probability. What I just want to observe is that actually I will concentrate it on this expression, but all the argument goes through the second one, because I can rewrite the second one simply as probability that minus xn bar it's larger than minus b. And therefore, I can apply all the arguments I will present today to this inequality just by exchanging x1 by minus x1 and a by minus b. So, as I said, I will now obtain an upper bound for this probability. We'll study these upper bounds. I will try to optimize over all upper bounds I will derive. So let me recall that m represents the expectation of x1, and we are fixing a larger than m. And now I want to obtain an estimate for the probability that xn bar it's larger than a, where xn bar is just the average of the first n terms. So I want to obtain this estimate. Okay, so let me fix a lambda positive. Let me multiply this inequality by lambda n and then take the exponential. So this inequality will become that I'm multiplying that by lambda times n. So here there is a 1 over n, which will disappear, and what will remain is a sum from 1 to n of xj, that this is larger than exponential lambda a n. So this is equivalent because the lambda is positive and the exponential is increasing. So now I can again use Chebyshev inequality. So you see that Chebyshev inequality is used quite frequently, and this will become minus lambda an. And now I have the expectation of this first term, so which is lambda xj, j from 1 to n. Now I can use the fact that these variables, so here I'm using the fact that these exponentials are, have finite moment, right? So this is why I need this assumption. So now I can use the fact that the random variable xj, so this is a product of exponential lambda xj. You can use the fact that these variables are independent just to pass the product outside the expectation, and then use the fact that these random variables have all the same law to get that this is the expectation of exponential lambda x1 to the power n. So this is equal to minus lambda a n, and here we have the expectation of exponential lambda x1, and this is to the power n. Right, so now that's very nice. So let me call m lambda. So if I fix lambda, let me call m lambda the logarithm of the expectation of exponential lambda x1. And this m, as you see, it's well defined for all lambda in R by assumption. So what I get here is that I can rewrite this expression as the exponential of the log, and when I place the log before the expectation, what I get is m. So this is equal to the exponential. Okay, let me still write it as an, and here, as I said, if I take the exponential log will give me m, so this is exponential m of lambda and to the power n, so this is multiplied by n. And putting together the exponentials, this is exponential n minus lambda a plus m lambda. So what we proved up to now is that the probability that xn bar is larger or equal to a, it's bounded by this exponential. Now if I take the log on both sides, I will get that the log of this expression is bounded by this expression, and if I divide that by n, I get that 1 over n log that the probability that xn bar it's larger than a, that this is bounded by minus lambda a plus m lambda. So this is what we proved up to now, and therefore the right-hand side does not depend on n anymore, so I can take the limit sup. So if I take the limit sup in n of this expression, it is bounded by the right-hand side. Now mind that the left-hand side does not depend on lambda, so I can optimize the right-hand side in lambda and say that this is less or equal than the infimum. And here we consider at the beginning lambda's positive. So the infimum over all lambda, well, of course, we could take lambda equal to 0 in this. By multiplying lambda equal to 0, we wouldn't go very far, but we can do that. So lambda larger than 0 of minus lambda a plus m lambda. And this is equal, so let me rewrite that. Let me take the minus sign outside. So this is minus the supremum over lambda larger than 0 of lambda a minus m lambda. And this will be my definition of IA. So let me define I of A as the supremum with lambda larger or equal to 0 of lambda A minus m of lambda. So if I define I of A by this formula, what I get is that this is equal to minus I of A. So what I proved is that, in conclusion, that the limit sup in n of 1 over n log the probability that xn bar is larger than a for any a larger than m, that this is bounded by minus I of A. So in the next take, I will start from this definition, and I will start to study the functional I of A, which I just defined by this formula. I just copy here what we proved. So we defined m of lambda by this formula. M is defined for all lambda. Then we defined I of A by this expression. And here, A, it's larger than m. And what we proved is this bound is that the limit sup of 1 over n log of this probability, that this is bounded by minus I of A. So as I said, I want now to examine this function I, and therefore the function m. And my first claim is that m, it's a convex function. So let's prove that. And for that, see that since we have all finite exponential moments, I can take the derivative with respect to lambda here. And so what we will prove is that the second derivative of m is positive, strictly positive actually. So let's prove that. Let's compute the first derivative of m. We have a log, so what we get is this is the expectation of exponential lambda x1. And this is coming from take the derivative of the log, and then we take the derivative over lambda of that, and this is the expectation of x1 exponential lambda x1. And this is what I will represent by the expectation with respect to a new measure of x1. So I'm defining here a new measure, p lambda, and p of lambda of a set A. So remember, p is defined on some probability space omega f. Now I'm defining for each lambda a new measure, p of lambda. And what is p lambda of A? So this is the expectation of the indicator set of A exponential lambda x1, and this is divided by the expectation of exponential lambda x1. So this is the definition of this probability measure. So I leave it to you to check that this is indeed a probability measure, so that for each lambda, we define in this way a new probability measure. And so this is what you see here. It's exactly then can be written exactly as the expectation of x1 with respect to this probability measure p lambda. And so this is m prime. So now let me take the second derivative of m. Here we have the numerator and the denominator. So let me first take the derivative with respect to the numerator. So I get an extra x1. So that will be the expectation of x1 squared exponential lambda x1 divided by the expectation of exponential lambda x1. And then when I take the derivative on the denominator, I get a minus sign, and I get the square. So this is the expectation of exponential lambda x1 and the square of that. And now the derivative of the denominator, so by deriving that in lambda, I'll get an x1 here, but I still have this term. So this will give me the expectation of x1 exponential lambda x1 and this square. So in terms of the probability p lambda, which I just defined, you observe that here what appears is that it's the expectation of x1 square with respect to E lambda, this new measure E lambda. And while here I have the square of the expectation with respect to E lambda of x1 square. So what appeared here, it's exactly the variance with respect to this measure p lambda of the random variable x1. And this is non-negative always, and it will be strictly positive unless x1 is constant almost surely. So if I add here an assumption that x1 it's not, so I'm not in the trivial case in which x1 is not equal to a constant almost surely, so this is strictly positive, which means that the function m it's strictly convex because its second derivative it's strictly positive. So we proved therefore that m it's convex, actually strictly convex, and when you have a convex function here and you define a new function by this variational formula, well, this variational formula, it's called the Legendre transform. So a French mathematician, Legendre, so it's called the Legendre transformation of the function m. And what I leave it to you to check is that if m is convex, then I is convex. So this is left as an exercise. So let me here add some properties. So my first observation is the one I just wrote, is that if m is convex, then the function I is convex. So I leave it to you to check as an exercise. Then the second observation is the following, is if I represent by L for Legendre m, the Legendre transformation of m, so this is the definition of I, right? Now if I apply L again, so I apply L to I, and if m is convex, this is exactly m. So if you apply twice the Legendre transform to a convex function, you get the identity. You get the same convex function, and this is a second exercise for you. Maybe I'll give a reference in the notes. So my claim is that if m is a convex function, and if you represent by L the Legendre transformation of this convex function, what I claim is that L2 it's equal to the identity if you restrict this application to the convex functions. So that's also an exercise. And then my third observation is that if I take a convex function m, or more generally any function m, and so now in my first observation and my second observation, m was convex, right? Now let's see what happens when m is not convex. Well, suppose that m is any function. What I claim is that I it's still convex, and if you apply twice the Legendre transform to m, so you obtain, applying the first transform, a convex function. So now you can apply the first observation. So applying by the Legendre transform again, you get still convex function. So L2m, it's convex. And what I claim is that this is the convex envelope of M. So remember, if you have a function which is not convex, so let me draw something like that. So this function, it's not convex. Well, the convex envelope of this function will be the largest function which is convex and bounded above by my function. So let's say that you have this function f, and you want to define the convex envelope. So you'll consider all convex functions which are bounded by f. So let's say that here you have a convex function which is bounded by f. And now you take the maximum of such functions. So I will draw here what would be the convex envelope. So that will be the convex envelope. And what I'm claiming here is that if you take any function m, you apply the Legendre transform twice, what you get is a convex function which coincides with the convex envelope of m, which is exactly the convex envelope. So these three observations are left as an exercise, and as I said, I will try to provide you with reference in the notes. And let me finish my observation with a fourth one. With a very useful bound. So let me take m function. Let me define by I, or denote by I, the Legendre transform of m. So I, it's given by this formula. Now, let me take A and lambda. And what I claim is that A, the product of A with lambda, it's bounded by I of A plus m of lambda. So that we have always this bound. And why is that so? Well, because I can always write A times lambda as A times lambda minus m lambda plus m lambda. And now I can estimate this difference by the supremum over lambda of this expression, and this is IA. So this expression is bounded by IA, and therefore I get the announced inequality. And well, that's very interesting because you see that you have a product, and you are able to estimate this product by the sum of two terms. So this is a generalization, if you wish, of the very well-known inequality that xy, it's bounded by x squared divided by 2 plus y squared divided by 2, the famous Young inequality. So you have here a generalization. So of course, this inequality, it's exactly that one if you take m to be the convex function lambda square. So if you replace lambda by lambda square over 2, what you can check, it's that I of A, it's given by A square over 2. So this inequality is nothing else that this inequality in the special case in which the function m of lambda, it's lambda square divided by 2. And therefore, this inequality generalizes this very well-known inequality. So these are the observations with respect to the function m I wanted to formulate. And now let's continue in our investigation of the large deviations upper bound. So remember, here's the definition of m, here's the definition of I. And now I want to compute mu. So I want to understand this supremum. So first, let's compute mu at 0. We know already that mu m, it's a convex function. Well, let's compute the value of m at 0. So at 0, it's taking lambda to be 0. Taking lambda to be 0, this expectation it's 1. You take log, becomes 0. So m of 0, it's 0. So let me draw here the graph of m lambda. So here you have m of lambda, and here you have lambda. And we know that m at 0, it's 0. So now m prime of lambda, we have seen that this is the expectation of lambda x1, where the expectation lambda, it's with respect to this probability, which is defined by that. So this is the expectation of x1 exponential lambda x1, and this is divided by the expectation of exponential lambda x1. This means that if I'm taking m prime at 0, so the derivative of m at 0, I just take lambda equal to 0, and that will give me that this is the expectation of x1, which is m. So this function, which I'm trying to maximize, so let me call maybe j of a lambda this function, which is lambda a minus m lambda. Well, there is a linear piece, and there is a convex. With the minus sign, it becomes concave. So j, it's a concave function. ja, for all a, it's concave. And this is the function we are trying to maximize over lambda. So instead of drawing the graph of m, let me draw the graph of j, a. So you see that at lambda equal to 0, we've seen that m of lambda, m of 0, it's 0. Lambda a, it's also 0, so it's still 0. Now, so let me write this. J a at 0, it's 0. And the derivative of j a at 0 will be, we have the linear part, so the linear part will give me a, and we have minus m prime of 0, which is m. And so you see that this is strictly positive because I'm taking a larger than m. So it has a strictly positive derivative at the origin. It's a convex function. So maybe let me assume, to simplify, that this m, what I want is that this function converge, well, that it has a derivative equal to 0. So this maximum will be given by the point at which j has, since j is strictly positive, if there is a point at which the derivative is 0, then this is the maximum of our function j of a. So let's see what is the condition for having a derivative equal to 0. So we are looking for lambda such that g prime of lambda is equal to 0. So that will be the point at which ja achieve its maximum, and therefore this will give us the value of I of a. So what is the equation? So let's see that this tells me that a minus m prime of lambda should be equal to 0. M prime, so what we want to solve is that m prime lambda, it's equal to a. But what is m prime? M prime of lambda, it's equal to the expectation with respect to lambda of x1, and this is also the expectation of lambda exponential lambda x1 x1 divided by the exponential lambda of exponential lambda x1. So now I want to add a new assumption, and this new assumption is that this function m prime takes all values between m and plus infinity. So I want to add this hypothesis that we have seen that m prime, so recall that m prime of 0, it's equal to m, right? Because m prime is this expectation when lambda it's equal to 0, so that's exactly the sorry, there's no lambda here, So expectation lambda of x1, it's this expectation. So if you take lambda equal to 0, this is just the expectation of x1, which is m. So m prime, it's m. And moreover, we know that m, it's a convex function, which means that the second derivative, it's strictly positive, which means that m prime is strictly increasing. So the graph of m prime so this is m prime of lambda. At 0, it's equal to m. So let's assume that m is positive. It could be negative. Doesn't matter. But what's for sure is that it is a strictly increasing function. So it starts from m. While it's strictly increasing, so it could have a finite limit. I want to avoid that, though this is not needed. Let's assume that this doesn't happen, which means let's assume that this function converges to plus infinity as lambda converges to plus infinity. So my extra assumption, so beside this assumption, I will now add this extra assumption is that the limit as lambda goes to infinity of m prime of lambda, it's equal to plus infinity. And so this is equivalent that the limit as lambda goes to infinity of the expectation of x1 exponential lambda x1 divided by the expectation of lambda x1, that this is equal to plus infinity. So I will assume this condition, and if you remember, in our example, I proposed two examples. The first example is the Bernoulli random variables. Well, this condition is not satisfied by this example. I leave it to you to check. So I cannot change the Bernoulli in such a way that their mean will be equal to a for a larger than 1. Since the random variables take only the values 0 and 1, the largest possible expectation you can produce with these variables is putting mass 1 in 1, so saying that the probability of x1 to be equal to 1 is 1, and that will give you an expectation equal to 1. You cannot find a lambda for which this expectation will be above 1. So these variables do not satisfy this assumption. But you can check that, and I ask you to check that our second example, in which we assumed that the random variables had a distribution given by Gaussian random variable with mean 0 and variance 1, well, that these ones satisfy this assumption. So let me assume from now on that this limit is equal to plus infinity, and please check that if x1 is distributed according to a Gaussian with mean 0 and variance 1, then this assumption is indeed verified. If this is the case, now I know that m prime is strictly increasing and takes value from, since it takes the value equal to I erased, but since it is equal to m, here is it. Since it is equal to m at 0 and converges to plus infinity, so it takes all values between m and plus infinity. So if you fix me a, I can find one and only one lambda for which m prime of lambda is equal to a, right? So under this extra assumption, we know already that m prime is strictly increasing because m is convex. Since now I'm assuming that the limit is plus infinity, I know that I can solve this equation. So that there exists, because this function, it's a bijection between 0 infinity and m infinity. Since a is larger than m, there exists a unique lambda such that this equation is satisfied, and lambda it's equal to m prime, the inverse of this function of a. So I solved this equation. Under this assumption, I know that there exists a point at which the derivative of j is equal to 0. So this coincides with the point at which j assumes its maximum value. And therefore, I know that I of a, it's equal to lambda, but lambda is given by this expression. So this is a times m prime minus 1a minus m of lambda, but lambda is given by that. So I have here a formula, an explicit formula for I in terms of the inverse of m prime. I, it's given by this expression and this assumption. You see that if this assumption is not verified, well, I know that m prime is strictly increasing, so it has a sup, the limit sup, let's call capital A, and therefore I could solve this equation for all a between m and capital A. So, okay. So that will tell me that actually for all I of, well, okay, as an exercise, I will ask you to drop this assumption and to see what happens in that case. So what would be my function I in the case in which m prime does not take all values, but has only, okay, so let me write what I'm claiming. An exercise, let me state that as an exercise. Remove this assumption. Let me call capital A, as I said, the limit as lambda tends to infinity of m prime of lambda. And what I claim, so exercise, show that if I take any a larger than a, maybe larger or equal than a, then I of a is equal to plus infinity. Okay? Then this supreme is actually equal to plus infinity. And therefore, this removes this assumption. But I don't want to enter into the details, so let's assume this assumption, and in which case we can always solve. And we get an explicit formula for I. So I have this formula, and I will just want to derive a relation between the derivative of I and the derivative of m by using this identity. So let me erase. And let me now compute the derivative of I by using this formula. So I prime of A will be equal well, so I have to derive this expression A. First, I get that this is equal to m prime, the inverse of m prime at A. Then plus, I have take the derivative here, so let's take plus A. And let me write this as the derivative with respect to A of m prime minus 1 at A. So this is the derivative of the first term. So let's take the second one. Then for the second one, well, I have to take the derivative of that with respect to A. So the first I have minus m prime, but this is computed at m prime inverse at A. So, and by the chain rule, now I have to take the derivative of this expression. And this I will write as dA of m prime minus 1 at A. What I want you to observe is that this second term cancels with the third term, because what I have here is m prime computed at the inverse A. So what I get here, that this expression is actually equal to A. So here I have A on both terms, and then the derivative with respect to A of m prime inverse at A. So this second term is exactly equal to the third term, but we have the minus sign, so they cancel. And what we finally get is that this relation between the derivative of I and the derivative of the inverse of m. So we have this identity, which follows from this explicit formula for I. So, okay, so let me stop here. So let me summarize what we did up to now. So we obtained this bound. So we proved that for all A larger than m, we have this bound. What is I? Well, to compute I is given by this variational formula, where m, it's this object. Now we proved that m, it's convex, and therefore since I, it's the Legendre transform of m, it is also a convex function. Now, I assume, to simplify, that m prime, that the limit as lambda tends to plus infinity of m prime of lambda, it's equal to plus infinity. So m prime, it's an increasing function. It has a limit. Let's assume that this limit is plus infinity. If this holds, then we proved the following equation for I, and we also obtained the following equation for I prime. Let me insist that this assumption is not needed. Well, if it doesn't hold, then this identity will hold only for A less than the limit of m prime lambda. Okay, but so let's assume that this assumption holds, not to bother with the other cases. Now, what I want is, well, I know that I is convex. So what I claim is that I of m, it's equal to 0, and that I prime of m, it's also equal to 0. So the picture is that you have here the mean. I is what's called the rate function of the large deviation principle. Well, the rate function vanish at the mean. Its derivative vanish also at the mean, and it's convex. Well, actually, you can prove that it's truly convex. Then it will look like that. So this will be our function I under this assumption. If this assumption doesn't hold, so what will happen is that you have here a value A at which, starting from this value, so the rate function will diverge to plus infinity on the left side of A, and it will be equal to plus infinity on the right-hand side of A. So that will be the picture if this assumption doesn't hold, but let's forget that for a second, and let's assume that this assumption holds. So this is the picture. So in order to confirm that, let's prove that I of m is equal to 0 as well as I prime of m. So I of m is the supremum for lambda of g m of, so remember that I called this expression GA of lambda. So this is the supremum over lambda larger or equal to 0 of Jm of lambda. So Jm of 0, if you take lambda equal to 0, we have seen that m of 0 is 0, so this is 0. But this is always true, even for, this is true for any a. And now let's compute Gm prime of 0. So Gm prime of 0, it's m, right? Because, well, we are taking here the derivative with respect to lambda, we get m. And then we have minus m prime of 0, but we computed m prime of 0. M prime of 0, this is equal to m. And so this is indeed equal to 0. So we have this convex function, J m, for lambda equal to 0. Its value is 0, its derivative is 0. And since it's a convex function, it will behave like that, and therefore the supremum in lambda will occur at lambda equal to 0, and will give me that indeed I of m is equal to 0. Okay, so this computation shows that indeed I of m is equal to 0. Now let me prove that I prime of m is equal to 0 as well. So let's compute I prime of m, but for that I will use this inequality, so this identity. So I prime of m, according to that identity, it's m prime minus 1 of m. Well, but m prime, what is the graph of m prime? We have seen that m prime, it's, so let me, right here, here's lambda. At lambda equal to 0, m prime takes the value m, which here I'm assuming that it's really positive, but otherwise it would be, it could be negative. So m prime is strictly increasing, so here's the function of m prime, and therefore you see that if you take the inverse at m gives you 0. So this is 0, right? M prime, it's a function, a bijection from 0 plus infinity in these two m plus infinity. Right? I leave it to you to check. We don't need this assumption in order to show that m prime is well defined, because by this, since I'm assuming that this it's finite, of course here I can put also x1 to any power. That will be also well defined. So in particular, m prime, it's defined from for any lambda positive, and its derivative, it's the value of the derivative at 0, it's equal to m. since m is convex, m prime, as I said, it's increasing, so strictly increasing. So that's a typical picture of m. And therefore, you see by taking the inverse that, well, since lambda 0 is sending to m, the inverse will send m to 0. And this is exactly what I'm writing here, is that the value of the inverse of m prime at m, it's equal to 0, which tells me that I prime is also equal to 0. So this is the typical picture of the rate function. The rate function will vanish at the mean. Its first derivative will vanish. And I leave it to you as an exercise also, just as an exercise to check the relation of the second derivative, so I second at m, with the variance. There is a relation. What I claim is that there is a relation between the second derivative at m with the variance of the random variable x1. So I leave it to you to check what is the exact relation between the second derivative of the rate function at the mean and the variance of the random variable x1. So this is what I wanted to present concerning the upper bound. We proved this inequality, and now I gave you the picture of this inequality. Of course, what I presented here today, I considered only the case in which A is larger than m, so we have this, let's say, first half, but you can repeat exactly the same argument as I said at the beginning, and then you'll derive the picture of I for values less than m. You put them together, and now you have the complete picture. And everything, as we said, for value larger than m goes through to values smaller. In particular, at m, I will be 0, and its first derivative on both sides will be equal to 0, which means that I will be differentiable at 0. And since it's strictly convex, the second derivative will be positive at m. And what I ask you to show is that there is a relation between the second derivative and the variance of the random variable x1. So in conclusion, what we proved here is the following, is that, well, this probability not only goes to 0, but it goes exponentially fast. So what we can say, or if we want to abridge what we just proved, we'll say that the probability that xn bar is larger than a, that this is approximately exponential minus n I of a. Right? We proved that, if you wish, that this is smaller than that. And smaller in which sense? In this sense. So to be rigorous, what this is telling us is that since this limit sup is bounded by this expression, it will be bounded by this expression plus epsilon. So for all epsilon, there will be n0 such that this expression is bounded by that one for all n larger than n0. So if I want, so this is true, now it's really true. So for all epsilon, there exists n0 such that if n is larger than n0, then this probability is bounded by that one. And this is what we just proved. So it's a very strong, right? It's not only true that it converges to 0, but actually it converges exponentially to 0, and the rate at which it converges to 0 is given by this convex function I computed at a. And you see that this convex function is strictly positive. Of course, at a equal to m, it vanishes. So if you take here m, you replace a by m, and this is 0. So this inequality is empty, has no meaning. if you take at a equal to m, yes, because for that we know that this doesn't vanish. So it's not true that the probability we can, actually what we proved here is for larger or equal to a, and we see that, well, this, if we replace a by m, this is not converging to 0 anymore, and therefore our bound cannot be a good bound. Of course, this is an upper bound. Maybe this upper bound is not sharp. Maybe we could do something better. And in the next lecture, I would get a lower bound to prove that indeed this upper bound, it's very, well, it's sharp. So this will be the theme or the subject of the next lecture.